so now we get to our definition of rank. So rank is just a short form or short way of saying what the dimension of the column space is. So mathematicians are lazy. So dimensions of column space is rank. We could always just say dimension of column space. So if I have an M by N matrix, then the dimension of column A, number of pivot columns, is going to be the dimension of row A, because pivot columns define where the row A is. All right, so let's look at our M by N matrix. So if I have rank A, that's dimension of the column space, so that's number of pivots, so that's basic variables. Dimension of dimension of null A is going to be the number of free variables, so that's non-pivot columns or free variables, and that's going to give me number of columns, and that's an N if it's an M by N matrix. So if I had an N by N matrix, then I could add to my invertible matrix theorem that the columns of A form a basis for Rn, that column A equals Rn, the dimension of column A is N, the rank A is N, because these are the same thing. Null A is 0, because there's no free variables, and the dimension of null A is 0. All right, so let's deal with the non-square matrices, because those are more interesting, actually more challenging. Okay, so let's make up, and I'm going to encourage you to just draw a 5 by 6 matrix that has 4 pivots. So I'm just going to put my squares in where there's pivots. So pivots, pivots, and one more pivot here. Okay, so there's my picture of my 5 by 6 matrix that has 4 pivots. So 4 pivots, that means that rank A is 4, right? Dimension of column A is 4. So what's the dimension of null A? So the number of columns is 6. So that must mean the number of free variables left over are 2. Okay, so is the column A in R5? So are elements of column A in R5? Yes, there are 5 entries. 5 entries in each column. Okay, so is column A equal to R5? So that means this is a way of saying, do column A span all of R5? Can I get to everything in R5 from linear combinations of my columns of A? No, there's not a pivot in every row. So cannot span R5. So there's a difference between in and equal to. All right, so let's look at this matrix. So I have a 4 by 7. So 1, 2, 3, 4, 3, 4, 5, 6, 7. And there are 4 pivots again. So I'll try and draw my pivots. There's another pivot. And one more pivot. 1, 2, 3, 4, 5, 6, 7. Okay, so there's it's a nice size. Kept the size with my sloppy writing. Okay, so is column A in R4? Are the elements of the columns have 4 entries? Yes, because there are 4 entries in each column. Okay, is column A equal to R4? Can I get to everything in R4 from linear combinations of the columns of A? Yes, because there is a pivot every row, so spans R4, right? The columns of A span R4. Okay, so is null A in R3? Well, it's a 4 by 7, right? 4 by 7 matrix. I know that there's 4 basic variables, so that must mean that there's 3 free variables, right? 3 free variables. So that means the dimension of null A equals 3. But does that mean that null A is in R3? No, it does not. So the elements of null A are the vectors that I'm going to multiply by multiply by A to get to 0. So these are the elements of null A. Okay, so that means what kind of elements, what kind of vector do I multiply by A? The size of A is 4 by 7. So the element, this vector x, must be a 7 by 1 matrix. So is null A in R3? No. Null A elements are in R7. Okay, how about this? Is null A equal to R7? No, right? Because there's no way you can say it spans R7 because I would have to have 7 vectors to span all of R7, and I don't have any information, so not at all. Don't know that for sure. I can't even, and I know, well, for sure, I know I only have 3 vectors, right? I only have 3 vectors, 3 free variables, because I have 3 vectors that are the basis for null A. And they're all in R7. So if I only have 3 vectors in R7, I can't possibly span R7.